All right, test one, two, test one, two. All right, hello. My name is Connor Druin, and I am here to provide a summary and critique of the academic study regarding the presence of microplastics in the ocean, performed by, and I apologize, I'm going to butcher these names, Qingsheng Xue, Guiting Yu, Fengqin Lu, and Yang Dong, as detailed in their paper Fluorescent Labeling Combined with Confocal Differential Raman Spectroscopy to Detect Microplastics in Seawater. All right, so to begin with a brief summary of the paper, the authors briefly discussed the quantity of plastic waste presence in the world's oceans today, approximately, according to them, 75 to 199 million metric tons. The team also defined microplastics as any plastic particle with a diameter of less than 5 millimeters and the ability to readily absorb heavy metals and pollutants. Various seawater organisms ingest these microplastics as part of their daily activities, and this obviously causes issues for the microfauna and macrofauna of the oceans. So the team had an initial choice to make when analyzing, figuring, quantifying how much of this microplastic existed. Um, Initially, they mentioned the idea of flotation by acid and alkaline oxidation, enzymatic digestion. Some of the equipment they considered using were scanning electron microscopy, pyrolysis via GCMS, and thermogravimetric analysis. However, they decided each of these methods were suboptimal for the purpose of their research, and so they decided on using Raman spectroscopy, as it had the ability to detect microplastics up to 1 micrometer. However, they also mentioned that one of the main issues with Raman spectroscopy in this regard would be the issue of fluorescence interference, leading the team to elect a form of differential Raman spectroscopy. So, in terms of actually collection of the samples, the team notes collection of the microplastic particles using sieves of successively smaller aperture, to get samples of successively smaller size. Um, these samples were then digested using 30% hydrogen peroxide solution and combined with Nile red for staining. In addition to the digestion, ultrasonic cleaning was employed, followed by a second density flotation using a sodium chloride solution of 1.2 grams per mil. So the team used fluorescence microscopy to determine an optimal concentration of Nile red. They determined 5 ppm as their optimal, and then incubated the samples at 40 Celsius for about 40 minutes. Shui and all discussed the length that they designed the at length the that how they designed the confocal micro Raman system for the differential Raman spectroscopy. To summarize, they used an LED that was co-laminated and focused on the sample, which then reflected light is imaged through a fluorescence microscope camera. They used a dual wavelength laser, which emitted wavelengths at 784 and 785 nanometer, with a 6 millimeter expansion through the lens. This Raman signal was then coupled into optical fibers by a Raman spectrometer, to collect the spectral information. The two laser wavelength excitation allowed for the team to acquire two different original Raman spectra without the background fluorescence interference. However, they also had to reconstruct these two original spectra to create the differential. The differential was determined by subtracting the two original spectra from one another. The reconstruction was necessary to eliminate any noticeable noise in the signal, which separated peak values and created an asymmetry. They also employed smoothing constraint operators, negative constraint operators, positive energy operators, to further improve this asymmetry, generating a final equation here, where Q, N, and P are the relative constraint operators, and alpha, beta, and gamma are the strength of said operators. So, concluding their analysis, the team mentioned how they used laser of 20 and 100 microwatts and acquisition time of 20 seconds. Using the accumulated data, the team generated a database of Raman signals for the identification of standard plastics found in these water samples. The determination was three types of plastics were sought after by the study. Polyethylene was the most abundant, followed by polypropylene and then polystyrene, with smaller unidentified samples also displaying a fluorescence. However, which would imply possible identities microplastics. However, they were too small to identify using their equipment. So, let's discuss the strengths and weaknesses of this study as I see them. So, starting with the strengths, um, the labeling and the differential Raman spectroscopy. Using the fluorescence labeling and Raman spectroscopy was a marked improvement over alternative methods, as the team discussed and as I discussed earlier. Um, because the differential Ramans addressed issues with detection times as well as the prevalence of false positives with the other types of identification. The team also using this system uh, shows very rapid identification of these microplastics between polyethylene, polypropylene, and polystyrene, and differentiating those from other possible contaminants besides the microplastics. These tests were also non-destructive, which is always a plus when considering analytical testing. And it should also be considered just the overall strength of the study itself is the environmental impact. Obviously, microplastics and plastics in general in the oceans is becoming more and more of an issue, and beginning to address that in a analytical way and being able to better identify the concentrations of these microplastics, it goes a long way to help the effort of preventing this in the future. But the study was not without weaknesses. So one of the largest weaknesses, in my opinion, was that this focused heavily on the near shore seawater range. They stayed within a few meters of the shoreline. There was not a lot of deep ocean testing. There was no deep ocean testing, and this is a limitation, as detailed in another paper, Jameson et al. As you can see here. Deep ocean species have been confirmed to contain significant amounts of microplastics in their stomachs, with an estimated of 72% of amphipods ranging from 7,000 meters, 10,000 meters affected by ingestion of microplastics. And just that those species alone show that microplastics go far beyond just the near shore range that this study focused on. The detection methods were also fairly narrow. As I briefly mentioned, the microplastics studied were polyethylene, polypropylene, polystyrene. However, these are not the only polymers present as microplastics in the ocean. For example, plastic water bottles alone contain polyethylene terephthalate, polyvinyl chloride, polymethyl acrylate, which this study did not focus on and was not analyzed by this. And another aspect of that is that the team openly discussed that there really is no standardization when it comes to collecting these water samples, and so that would also be a weakness that's not necessarily on the team themselves, but in general, there's no standardization here. It should also be mentioned the sort of accessibility and repeatability of this study is narrow because this is a special differential Raman spectroscopy that they created for this specific purpose, um, which hinders the ability of other researchers repeating the study and confirming uh, the original team's estimations. My possible suggestions for the future with this are fairly obvious. Expand the range. Expanding the range of how deep in the ocean you go, more than the shoreline. Even if it's not necessarily 7,000, 10,000 meters, as that becomes fairly difficult, but going further into the ocean to get deep water samples beyond just narrow shoreline. um, Types of plastics obviously would be ideal to be expanded upon more than just, while some of the more common plastics, polyethylene, styrene, polypropylene, um, are going to be prevalent. There's other types of plastics that should also be considered. And then standardization. I mean, method standardization, sample size standardization. These would be aspects that should be addressed to further these types of studies and further the influence of these types of studies, so that we get a better understanding of just how much plastic is being leached into the ocean by waste plastics. So I wanted to sort of close here by just mentioning, why ramen. Like, why would ramen work best for this over other types of analyzation or analyzing. Um, so as the team sort of touched on, they used pyrolysis, GCMS, or they considered pyrolysis, GCMS, SEM. Um, but each of these would be less than ideal for different reasons. For example, pyrolysis would be less than ideal because of the you know destruction of the samples, the breakdown of the samples, which would hinder any sort of ability to truly quantify the concentrations of each individual type of plastic. Um, SEM alone would, while this study did integrate microscopy, um, SEM alone would be better for just understanding the morphology of the plastic, while not being great at determining the concentration or even identification of the different types of plastic. Another one they briefly mentioned was DLS, dynamic light scattering. While this I think has potential, this would be better for even smaller plastics, smaller than the 1 micrometer they were looking for. However, while it could look for smaller plastics, dynamic light scattering isn't great for larger sizes, so it would have to be some sort of integration of both. So overall, ultimately, I think the article presented a very promising technique for potential significant environmental benefits, though practical implementation right now and broader applicability would require further exploration. Anyway, thank you. I hope you all enjoyed this summary and critique. Thank you very much.